So good day. So our topic for today is still a continuation for our discussion in the subject. We are now dealing with parallel AC circuits. So in parallel AC circuits, we know that the voltage is a in the parallel circuits the voltage is equal. Okay, so in the parallel circuits, for now is instead of having a voltage triangle in the last topic, which is in series, now we have now a current triangle because it is in parallel. The current is not constant. Now for our example, last time we have tried an example related to this, but it is in the long method. But for now, we are going to utilize the shortcut method. So in the problem is we are dealing with resistor and inductance. We know that a resistor is connected in parallel with inductance, so its voltage drop across them is equal to the power supply natin or voltage supply, which is 60 volts, and the current is not constant. So first is we're going to use a node to create a circuit diagram. So this is our first impedance. The second one is our second impedance. Okay, let's have a recap or a review first. We know that in AC circuits, the impedance Z, it is equals to the resistance positive negative xj, right? And we know that the positive and negative, it depends if it's either capacitive or it is inductive. No, but in our case is since it is inductive, the its impedance is Z is equals to R plus xji. Okay. Okay. So in the problem, so for each circuits, we must think that it is no, for each branch it is a pure resistive, and the second impedance is pure it is pure inductive. So we could say that this is our Z sub 1. So this is our E, this is our power supply, which is equal to 60 volts. So this is our Z sub 2, or our second impedance. So our Z sub 1 is equal to 20 ohms. And our C sub 2 is, this is for, uh, our C sub 1 is, since it's pure capacitive, if we will create here a plus, this is 0 because it has no reactance. So it's 0, so still it is still equal to 20 ohms. Now, for our Z sub 2, our second impedance is it's the pure inductive, which is 2.38 millihertz. We are going to convert this into its inductive reactance. So the inductive reactance, again, we know that X sub L, or the inductive reactance, is equals to 2 pi FL. So using our calculator, so we could say that the inductive reactance is 2 pi 1 times 1000, which is our F, 1 kilohertz or 1000 frequency, and then 2 pi 2.387 times 10 raised to negative 3 or millihertz, and it is equal to 14, or we could round it off into 15. So our X sub L is equals to 15 ohms, or if so this is the X sub L. Now if we're going to put it into, so it has no resistance, so it is 0 plus uh 15 J. So based on the rectangular form of the impedance, the general rectangular form of the impedance. Okay, so R plus X J, since we are dealing with inductance, that is why it is plus. Okay, so it is RL parallel circuit. Or in other words, I could we rewrite this into, this is equals to 15 J. So positive because it is inductive. Now, uh, just applying the basic to get the total impedance, the same with what we are using in the DC circuits when we are dealing with parallel resistances is we have a formula which states that um the total impedances is equals to the sum of the reciprocal no, the reciprocal of the total impedances is equal to the sum of the reciprocal for each impedance. So therefore with this, um to get the total impedance, the total impedance is equals to the one of the derived formula for the impedance is 1 over z sub 1 plus 1 over z sub 2. So therefore, our total impedance, or our z rather, this is equals to 1 over, our first impedance is 20, and our second impedance is 15 I. Now again, if you're going to calculate, so 1 over 20. So plus 1 over 15 I. Sorry. So take note that your calculator must be, it should be in complex form so you could calculate it well or perfectly. So 1 over 20, okay, plus 1 over 15 I. Okay. Now, so it is equal to the our impedance is equals to 7.2. This is equal to 7.2 plus 9.6 plus 9.6 I. Okay. Now, uh, next is we are going to use, uh, our goal is to solve for the current for each branch. So what we need to do is, since we have the formula for our I is equals to the supply voltage over our impedance. This is our Z here is the total impedance. So the same with our total impedance. So again, in our circuit is, we know that our E is equal to, this is equal to 60 volts. And we know that this is equal to the voltage drop across the resistor and also equal to the voltage drop across the inductance. Now, I'm using the basic formula for the current, which is equal to the voltage over the impedance. So just use the formula, it's direct substitution. Our voltage supply is equal to 60 volts, and our impedance is 7.2 plus 9.6 J. So our current is equal to, using your calculator, so 60 over our impedance, or I will input the answer already, since the answer is our previous answer is 7.2 plus 9.6 J. So in order for me to shortcut, so hindi na ako mag-type. So our answer is at 3 minus 4 I. So our current is at 3 minus 4 I. Okay, now we know that in the impedance, it is equal to resistance plus the in reactance I, and also in terms of its current, uh, since they are just analogous and their phase angle is also the same, so this is why our current our current is also equal to the current that flows in the resistor plus uh the current that flows in the inductor I. Okay. Now, since okay, so in the current, this should be minus. Okay. This is minus. It's because lagging, this is lagging. Okay, for the impedance in inductive circuit is plus for impedance, but in the current it is negative. It's because lagging. Okay. So now, so in the problem, our answer is 3 minus 4I, which means that our 3, this is the current that flows in the resistance, or our Z sub 1, and also therefore is the current that flows in our inductance or inductor. Okay, so now therefore from this equation, um, in our problem, we could get its total current by converting the complex form, by converting the rectangular form into its polar form. Shift to 3. So now we get 5 of negative 53.13. So this is also equal to 5 of negative 53.13. Okay, so we know that this one is equals to I, the total current, times the phase angle. Okay, so therefore we could say that this is our I sub R, and the 4, this is our I sub L. So minus is an indication that the circuit is inductive. So it is inductive. So this 5 ampere, this is our total current, and our uh, theta is a negative 53.13, or this is positive 53.13. The sign negative indicates that it is lagging. Okay, so the 5 is, this is our total current, and this our phase angle. Our phase angle is 53.13. The negative sign again is indication that it is lagging. Now, in our impedance, if we are going to get the impedance, so meaning that in the current in each branch, so using only the total impedance and the total voltage, or the voltage supply, we could get its current, right? So to make it in a shortcut method, so using the rectangular form, or complex form rather, our complex method, the current in each branch, we could get also, if we get the total current impedance, no, the complex form of the total current, we could get also the current that flows in each branch. Example for this, we get the current, which is that the total current is equal to the total voltage over total impedance. Our 60 volts is for the total voltage. Our total impedance is 7.2 plus 9.6 J. Again, this is a parallel circuit, and we must apply the law, or the principles, or the characteristics of simplifying or finding the total impedances using the parallel AC circuits. Now, 60 over 7.2 plus 9.6 J, we get its rectangular form current, which is 3 minus 4 J. Again, the 3, this is our using also the rectangular form of the current, is I sub R is 3, I sub L is I sub 4, and then if the rectangular form for the current, we are going to convert it into its polar form, we get the total current and its phase angle. Now the total current is 5 ampere, and then the phase angle is 53.13. The negative is an indication that it is lagging. Now we already get the letter A, and we get also letter B and letter C, and letter D is not yet, because the 7.2 is the total resistive, um that this is the total resistance, the total combined resistive element in the circuit, and 9.6 is the reactance. This is the total reactance, which is the combination for the two parallel connected elements. Now, if this if the impedance, since this is the rectangular form, if we could be able to convert this one into its polar form, this is the equal to Z angle says pala of phase angle. Okay, this is the phase angle. So this is a negative in for our this is negative for our current, positive for the impedance, negative for the phase angle for the current. So the indication that it is lagging or leading is we are depending on the current, okay, current, not in the impedance. impedance is just a resistive element. The current, it has a direction and magnitude. Okay, so so therefore, our total impedance, our Z or Z sub T or Z equivalent, we could convert it into its polar form, so we could get the total impedance. So 7.2 plus 9.6 I equals, and then shift to complex form 3. So this is a polar form. This is equals to 12 of 53.13 says. So this is equals to 12 says of 15.13. So now this is our Z. Okay, so to make it short, so from the given to we have resistor and our inductor. Our resistor, this we could convert it into a impedance, since it is this is a pure resistive element. So Z sub 1 is equals to 20 ohms, since plus 0 I still it is 0. Now in the second, it is a pure inductive. In the second branch, it's pure inductive. So we have a 0. So our resistance is 0. So 0 plus 15J, or rather it is equal to 15J. So using this combination combined to get the total impedance, we get 1 over 1 over Z sub 1 plus 1 over Z sub 2, or you can use other method to calculate for the total impedance. So this is equal to 7.2 plus 9.6J. So using this, use the current formula, voltage over impedance, we get the current, the complex form of the current, and convert it into polar form from rectangular to polar form. Now this is the I sub R, I sub L, the total current, the phase angle, and then we convert the rectangular form of the impedance to a polar form. Now we get the total impedance, and this is also the phase angle. They are in the same phase angle. Now, if you're asking, sir, why does the design for the impedance and the current is the same? It's because for the impedance, it should be plus, because it is the principle of the impedance. For inductive, it is plus. But now, in terms of our I, since the denominator is Z, uh, if the sign here is plus, therefore it's when we divide it, its angle is negative. So as a preview for the capacitive circuit, so or it is pure capacitive, if the impedance is negative here, so its sign for the current is plus, which indicates that it is leading, as what we have tackled in our first lesson. Okay, so just focus on the current. The current is an indication for the lagging or leading of the circuit. Again, the impedance, this is just its form. So it has no direction, or it has no direction, it has only magnitude. So just focus in the current, because we are dealing with AC circuits with direction and magnitude. So that's all. So I'm not sorry. So for the last one is we are solving for the power consumed. So it's up to you what would be the formula that you are using. So to get the power consumed, um the power consumed is we are using, so to make it short, so we could get all the power related in this example. So we know that our apparent power is equals to the total voltage times the current. So our apparent power is our voltage power supply is total is 60 volts, and our current is 5 sets of, so 5 um sets of negative sorry, so 53.13. Again, let me remind you that the current here, it should be it is what we call the conjugate current, meaning when we are using this current, if the total current, or the current, or the polar form current for the circuit is negative here, lagging, so you should conjugate the current from negative to positive. Okay, so that is the principle of using this formula. The apparent equals E times I. Okay, so meaning if you are use so meaning if we are dealing with capacitive circuit, so if it is plus here, you're going to make it negative here. Okay, so um therefore our okay, let's see. So therefore our apparent power, the rectangular form of the apparent power is this is 60 times 5 sets of 15.13. Okay. Again, so let us review also that the apparent power, it is also equal to the total power in watts plus minus the reactive power J. Now, whenever we get the rectangular form of the apparent power, we can say that the first term here, that is the term without J or I, it is the total power in watts. While the other term is the term with J, it's either plus or minus depending on its capacitive or inductive. The Q is the reactive power in VAR or volt ampere reactive. So in our problem, so equals the value for our 289.6. Okay, our current, so E times I, 5 times total power. Okay, so our voltage source is equal to mm, okay, our voltage is 60 times 5 of 53.13. Okay, so in our problem, so 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 in our next goal is to solve for the apparent power. So to get the apparent power, so in our problem, so let us review that the apparent power is equals its rectangular form is equal also for the total power in watts, positive, negative, the reactive power J. So our S basically it is equal to current times the total current times the total voltage. So 60 volts, 5 of 53.13, using our calculator, that is equal to 180 watt, 180 plus 239, 213, 240 plus 240 I. And also if we could convert this into its polar form in the above, so in here its polar form is this is equal to the total apparent power says of its phase angle. So therefore, in our problem, if we convert this into its polar form, this is equals to of 300 of 15.13. Now, in our problem, what is asked only is the total power in watts, but this time, take note that the consumed power, it is only the power, this is only the true power in watts. But in what our solution is, we use the rectangular form of the apparent power, so which is 60 times 5 times 53.13, which is equal to 180 plus 240J. And so this is the rectangular form. We convert it into its polar form, which is equal to 300 sets of 15.13. Now we know that our 180, this is our true power, plus the 240 is our reactive power. And then in terms of polar form, the 300 is the apparent power. And the angle here is the phase angle. This is the true power in watts. This is uh, a reactive power, and this is our apparent power, and this is our phase angle. As you observe, the phase angle for every total parameters or components is its phase angle is the same 15.13. Okay, so that's all for the example number one. So thank you for listening. Okay. For our second example is our given is we have a 30 ohm resistor, and also we have inductance again. So the total resistor, no, no, I mean is our resistor, which is a 30 ohm resistor, is connected in parallel with a pure inductance of 3 millihertz. Okay. So in our problem, so first again is we must create a circuit in order for us to visualize the parallel circuit. So this our supply voltage. Our supply voltage is 110 volts, and the frequency is 2000. Now, uh, our first branch is 30 ohms. We can say that that is our first impedance, our Z sub 1, Z sub 1. And for the next, so our Z sub 1 is equals to, this is R, this is R plus xj. So we know that we don't have we don't have a reactance, so that is why it is equal to 0. So therefore, our Z sub 1 is, since it is pure resistive, it is equal to 30 ohms. Okay. Now, so for our second impedance, which is for our second branch, is 3 millihertz. So this is our second impedance, which is equal to a Z sub 2. Nathan. Okay. Um, since we are dealing with the inductance, which is first we must get its inductive reactance. So the inductive reactance X sub L is equals to 2 pi FL. So therefore, our X sub L, so using our calculator, our frequency is equals to 2000 hertz or 2 kilohertz, and the inductance is 3 millihertz. So using our calculator, um, uh, 2 times, sorry, so 2 pi times 2000 times 3 times 10 raised to negative 3. So with this, we could get the inductive reactance, which is equal to 37.7. Okay, so our inductive reactance is 37.7 ohms. Now, in our second branch is it is dealing only with inductance, so we can say that it is pure inductive. So as stated in the problem, that it is pure inductance, so meaning it is pure inductive. So therefore, uh, we don't have a resistance, so the resistance is 0. So therefore, this should be 0 plus uh 37.7 ohms I, okay? Or rather, we can say we neglect the 0, this is equal to 37.7 I or J. Now, simplifying the circuit, we are going to combine the Z sub 1 and Z sub 2 by applying the characteristic or the rules in combination of the parallel circuits. So therefore, our total impedance is equals to 1 over 1 over Z sub 1 plus 1 over Z sub 2. Okay, so we know that our Z sub 1 is equal to 30 ohms and our Z sub 2 is equals to 37.7 I. So using our calculator again, so we could get the total impedance by combining the two impedances. So is 30 ohms, our Z sub 1, and our Z sub 2 plus 1 over 37.7 I. 37.7 I. And then we get the rectangular form of the total impedance. So our 18.37, this is 18.37 plus uh 14.62 I plus 14.62 I or J. Now we know that this is the rectangular form. We could get also its we could get also its the polar form. So this is the rectangular form. So we could get its polar form by converting the rectangular form into its polar form. Shift 2 3. So this is 23.47 says of 38.51. So it is equal to 23.47 of of 38.51. Okay, now we know that the 18.37 here, this is the total resistance or total resistance combination of the two. 14.62 is the total this is the total inductive reactance. Now the 23.47 here, this is already our total impedance, and this is our phase angle already. Okay, so next is we're going to solve for the current. Our current is basically this is equal to the voltage source over the impedance. Our current is equals to, this is 110. Our given power supply is 110 and over the rectangular form or the polar form. So you can use this one or this one. It's up to you. So I will use 18.37 plus 14.62 J. So therefore, our I or our total current, we could get the first the rectangular form of our total current. So this is 110 over ans or the answer. So this is my previous answer. So this is the technique. So no need to type the previous answer. So it will automatically appear here. Okay. So therefore our uh 3 point 3.67 minus uh 2.92. So this is 2.92 J. Again, we convert this into its polar form using again the shift 2 3. We could get its polar forms 4.67. So 4.67 of a negative 38.51. So negative 38.51. Now next is we get the power. So the power of the circuits is E times I. Again, this is a conjugate current. So if we are using negative 38.51 for our phase angle, if we are going to substitute this in here, we are going to conjugate the sign from negative to positive. Now, so therefore, our apparent power is equals to 110 of 4.67 of positive 38.51. So we are using the conjugate current. So therefore, our apparent power is the rectangular form for our apparent power is this is equals to 110 times 4.67 of 38.51. So therefore, our 401.97. So this is 401.697 plus 319.86. So 319.86. So 319.86 J. And uh, so first is let's calculate for the current in each branch. So now we get already the current for each branch. So the 3.67 is uh, this is our this is our current I sub R, or this is the current that flows for our Z sub 1 or the first impedance, or the our 30 ohm resistor. Our 2.692, this is the current that flows in the I sub L, or for the current that flows in the inductance. Our 4.67, this is the total current I, and this one is our phase angle. Again, negative is an indication that it is lagging. The 23.43, this is our total impedance. This one is the same. This is our phase angle also. And for our apparent power, uh, the 401.97, this is our true power. And this 319.86, this is our reactive power. Okay. So this is in terms of watts. This is in terms of volt ampere reactive. Now, if we're going to convert the rectangular form, converting the rectangular form, this one, into its polar form, we could get the total apparent power, which is equal to 513.7. Where is it? 513.7 of 38.51. Okay, so this is our apparent power, and this is also this is saying this is our phase angle. Now, let's check our problem or solution if it's correct. So given the solution. So in the problem is we have already our answer. 3.67 is the current that flows, in the um first impedance. Okay, so in our circuit here, the current that flows in here, this is our I, our total current, and the current that flows in here, it is our I sub R, and the current that flows in here is I sub L. Now, in the circuit, since it is parallel, the current that flows uh, leaves the power source is the total current. As it enters this node is an indication that it is in parallel, or it has two or more branches connected. So the total current will be divided by the I sub R and I sub L. The other portion or the other part will travel for our Z sub 1, and the other is for Z sub 2. So that is our I sub L, and I sub R and I. Okay. So 2.92 is for our I sub L. Letter B, the circuit current is 4.69. So my answer here is 4.67 because I use the I use this one. It has no it is lacking of decimal places. I suggest if you are solving, try to use at least four decimal places so you must arrive with a more precise answer. So the angle, the phase angle is 38.51. So it is lagging. So the lagging is an indication if it is negative, or rather if it is inductive circuit, it is pure inductive only. It has no capacitance, so it is lagging. Okay, so for the power naman, so in our power is we are only trying to solve for the total power, the true power, but still we get the reactive power in shortcut or a short method, and also it's the total apparent. So if possible, so what if in our next exam or quizzes, you're going to solve a lot of variables like the apparent power. So this is a more shortcut or more advantageous technique, so you could get all variables if possible. So the rectangular form is here. So this is the true power 401.97. So if you observe, there's a big discrepancy for 104 here. So in our answer is 401.97, but it is acceptable because say in our problem, in our here is we are using only two decimal places. So I suggest again next time if you solve, try to use at least four decimal places. So this is our example number two. So I hope you understand. So if you have questions, kindly send a message to me, so, or if you have clarifications. So thank you for listening again. God bless. Okay. Okay, so for our third problem example is still a resistance and inductance connected in parallel, but our problem is it is more different in compared to the first two problems that we had a while ago. It's because in our current problem is we don't have an inductance. So meaning there are some different method that we will acquire. But still, we are using the concept of the complex method, complex mode. Okay. Now, first, we must first understand how would be the relationship of the currents in terms of its what do you call this in the it's a phasor diagram. What would be the relationship of the current for the inductance, resistance, and the total current? Okay, so we know, okay, first, um, it was stated, it was there in your handout, the relationship already, but still I'm going to discuss the the concept of the three currents. Okay, so first is it's about the voltage. We know that the voltage is our the voltage supply or our E. We know that this is the reference the reference element for the AC parallel circuits is because the voltage is constant. Now, what matters now is in terms of current, it's either lagging or leading. It depends on it is what component is available. If it's more on inductance, so meaning if it's inductance, it is lagging. If it's capacitance or capacitive, it's leading. Now, since we our given is it's dealing with inductance, so meaning it is lagging. Now, the phasor diagram for the current here is of course the current our I sub L sorry our I sub L our I sub L is our I sub L our I sub L it lags 90 degrees from the supply voltage. Now the question is, so what the where would be the our I sub R? Our I sub R is our I sub R, it is in phase with the total voltage. This is our I sub R. Now, if we are going to get its resultant force, oh no, the resultant current, which is already our total current, again, in AC circuit, the resultant is the total or the sum of the two components. Now, if it gets, if in at the center, if we could have here combination of the two. So this is our I total current, and this one, this is congruent with the our I sub L. So this is also here is our I sub L. Now we get the right triangle in here. Okay, so meaning with this we could say that the total current is also related with the Pythagorean theorem, or since it is a right triangle, our total current is equals to the square root of I sub R square plus I sub L square. So that is the principle. So meaning if in our problem our I sub R in the what would be the direction of the I sub R? So we know that the I sub R is in phase with the total voltage. It is always zero. Okay. So our I sub R, its phase angle of no, its angle or direction always at 0 degrees. While our I sub L, it is always I sub L of this always negative 90 degrees. It's because it is lagging. Now, in our previous problem, what the phase angle that we are talking is it is in terms of the total current. Okay, so it depends on what would be the direction of the total currents. It depends on the problem. Okay, but for the current that flows in the resistance in RL parallel AC circuits, it is always zero. It's because it is in phase with the total voltage going east. It's zero. Also, for our I sub L, as based on its concept that it is the inductance is lagging, or in the parallel circuits, it lags 90 degrees from the total voltage or the supply voltage. Okay, now let's go back with so I discussed this concept. It's because it is related with or it is important to know the concept behind it because it is applicable for every parallel AC circuits. Okay, so in our problem, again, if we could be able to create a circuit diagram, uh, our given is we have a voltage supply of 200 volts, and then we could create so our first impedance is a PR resistive, which is equals to 40 ohms, and then our second impedance now, our Z sub 2 is based by inspection, we didn't have an inductance, so meaning that our X sub L is still unknown. Okay, so what is asked in the problem is it is equal is the inductance. So we know that the inductance is just related with the inductive reactance. So the inductance is just related with the inductive 2 pi FL, inductive reactance. And now by inspection, our frequency is given, X sub L is not yet given also. So we must look for a solution that could solve for our X sub L. Okay, so uh, in our problem is uh, we are having already our Z sub 1, so we could get the current I sub R is the same with our I sub 1, or the current that flows in here. So it is just a subscript. Okay, knowing that the I sub 1 is it's the current, or the current that flows here is the current for that flows in the resistor 40 ohms. Our I sub R is equal to our power supply over the impedance D sub 1. So I sub R, or I sub 1, is equals to 200 volts over 40 ohms. So therefore, our I sub R, so this equals to 200 divided by 40 is 5. So this is 5 ampere. It's 5 ampere. Again, angle, it is always 0 degrees based on its principle. Next, uh, to get the X sub L, we know that the X sub L, to get the X sub L, we know that the only formula that we have is it is related with our X sub L is related with Z. It's because x sub lj is equal to z sub 1 based on it's our method that we are going to use the rectangular form. So with this is to get the c sub 1 is first we need to get the what do you call this? Okay, so to solve for our z sub 1, so using this one, so we know that to get the z sub 1, we know that I sub 1, oh no, I sub L, sorry, or I sub 2 or I sub L is the same. It is equal to E over Z sub 1. Now, basically, we don't have this out, or sorry, so this is Z sub 2, Z sub 2. Basically, we don't have we don't have the value or any way to solve for the z sub 2, but instead we could get the I sub L. It's because I sub R and our total current I 8 ampere is given. Okay, so using the formula for the Pythagorean theorem as what we have derived a while ago, so our I sub L, basically I sub L is equals to the square root of I square minus I sub R square. So our I sub L is equals to our given supply current is 8 ampere. So it has no angle. So it's okay lang. So it's negligible. Hindi siya kailangan. 8 square minus I sub R is 5 square. So therefore our I sub L is this the square root of square root of 8 square minus 5 square is equals to 6.24. Our I sub L is 6 point, so 6.24. Again, the angle is always negative 90 degrees for the inductance, the current. So it's because it always lags negative 90. No, it always lags 90 degrees from the, or negative 90. Now, at this time, we could get the uh, z, our z. So we can erase this one. Now we could get the our z sub 2, which is equal to x sub li. So therefore, our z sub 2 is equals to 200 volts over our current, which is 6.24 I sub L of negative 90 degrees. Our z sub 2 is equals to, this equals to 32 point, so 200 over 6.24 of negative 90. So, why I am putting the 0 degrees here as negative 90 degrees. In a way, yes, it is okay. So you can calculate the current without this one, but still it is important for it's important to know the concept. Says what if in our upcoming quizzes we will have some questions about it, so you can answer. So 32.05, so 32.05 I. With this we can say that our 32.05, this is our x sub L. Using this, now we could get our L. So our L is equals to the inductance is equals to x sub L over our 2 pi f. Our x sub L is 32.05 J. Sorry. Oh, it's okay. It's okay. You can neglect the So this is if you could get its polar form is equals to 32.05 angle of 90 degrees. Okay, so therefore we are using the pure in the magnitude 32.05. So over So 2 pi 50. So our inductance is equals to 102 millihertz. Now, again, so there are maybe there are some methods that you are going to use or utilize. So it's okay. So for now, I'm just having a consistent type of solutions from based on our first example and second example. So I am dealing all of my uh, steps in solving is I use the complex mode. So again, so it's up to you where what would be the depends on the problems that you're going to use. So maybe there are some solutions that might be more easy for you to solve. So it's you could use that. So it's up to you. So what would be what is more preferable in your side. So that's all. So this is for our example number 3.